Good evening and welcome, everyone. I am Deb Raybergen. I'm Vice Dean for Advancement for the School of Arts and Sciences. I'm excited to welcome you to our February edition of Penn Science Cafe, titled Even a Physicist Can Learn to Knit, Unraveling the Science Behind Sweaters. With sweater weather in full effect, we couldn't have timed it more perfectly. Before we get started, I want to note that the Penn Science Cafe is generously funded by the Adolph and Felicia Leon Fund, which supports Penn Arts and Sciences programming. Now, for the bit, I had to put on as many hand knit items as I could. So let's see if you can name the patterns by the end of the program. I bet you some of you can. But I, yes, did make my sweater, and I see several of you have things that you have made as well. But although I know how to purl and work cables, I don't know anything about the physics behind the craft. The centuries-old practice is deceptively complex, influenced by geometry and materials. So here to enlighten us all is Randall Kamien, Vicki and William Abrams Professor in the Natural Sciences. Professor Kamien is a theoretical condensed matter physicist, specializing in the physics of liquid crystals. His lab has closely studied kirigami, the Japanese art of cutting and folding paper to create 3D designs, to better understand the deficits of crystals and the mathematics behind the defects in crystals and the mathematics behind such quirks. Those findings can then be applied to real-world scenarios, providing critical breakthroughs in medicine, design, architecture, and a number of other areas, including, to our delight, knitting. Professor Kamien will discuss new research that ascribes mathematical language to the stitches that keep us warm during the cold winter months. Following the presentations, we should have plenty of time for questions, but first, please join me in welcoming our speaker.
Hi, so, well, I hope I just don't disappoint anybody about what it is that I know and don't know. But let me just start by saying, here's my team. I just want to say, here's the team. I've worked with a lot of people over a lot of time, with a team that is both at the University of Pennsylvania and Drexel, and now people have moved on to other places. Oh, careful. Okay. And in the audience, you'll find some of the team. Well, you'll find Warren and Isabella. They're here. And the real inspiration behind this is Genevieve Dion, who's a professor of design at Drexel. And you'll hear more. And we've been funded by various organizations. This is an old slide. I don't know if you know if this exists anymore. Anyhow, it doesn't matter. So knitting is really hard, okay? Very complicated. And you can tell because, first of all, there's all these different yarns. And, for instance, I can detect some yarn instantly because I'm allergic to wool. But not Angora, not cashmere's okay. Right? Yeah. It's sheep wool. It's lanolin. It's the lanolin. Okay, right? And so if it's not well washed, I will get itchy. But the yarns are very complicated. There's nylon and poly whatever and elastane and cotton and wool, and they're all different. And people who knit all know. Oh, there's seat. Don't sit on that lens cap. Okay, you're good. Okay, there's people who knit know that each different kind of yarn behaves differently, and different kinds of yarn will end up making different kinds of feelings and materials, and they all know that. Somebody, I can hear that from people, right? They also can make all sorts of things. They can make these complicated patterns. This is like called a cabling. There you go. You're all nodding. Good. Okay, cabling, right? And ribbing and stuff like that. And then even more complicated, to me at least, is that people knit with multiple needles, right? And I'm not even sure which needle they're supposed to be holding. I don't know how they would keep track. I had a student, Sabeta Matsumoto, who's a professor at Georgia Tech. She studies knitting. But she used to knit, like some of you in the audience are. She would knit in the audience. And she had these incredibly complicated, because how did you keep track of where you were, right? I just couldn't imagine how you would do it. So I always viewed this as impossibly difficult to understand knitting. So how do you knit something? If you want to make a sweater that feels a certain way and has a certain pattern and looks a certain way and fits a certain person, what do? Okay? Well, you ask a guru. Okay? You can tell the guru, and you can go on the web, and there are gurus all over the web. Okay? Has anybody here heard of any of these 5 gurus that I found? No? Oh, you have? Okay. Which one? Taylor Earl. Okay. Yeah, so there are all these different gurus who you can get on the web and they'll tell you exactly what to do. Oh, if you want to do this, use this kind of fabric or this kind of yarn and this kind of stitch. And here, see, bunny. Okay, bunny is going to be a theme. It was, it started at the Super Bowl, and now you'll see bunny theme. So you consult a guru. And so how do you start, right? You learn from somebody who knows, right? It's very difficult. It's not impossible, but you could get a book, right? It's like you could learn to drive your car by pulling the user's manual from the glove compartment. Oh, this is how steering. It actually has all the instructions about steering and braking and how to drive. Okay. And this is very much like how you do physics. Physics is very complicated. And how do you start? Well, what you do is you consult gurus there, okay? And here's Kip Thorne in his guru costume, you can see. And here's Murray Gell-Mann writing numbers, because, he and, Einstein. And anyone know who this is? It's Katherine Johnson, right? Who could calculate the trajectory to the moon and back in her head. Okay, and here's Emmy Noether, who even Einstein thought was scary brilliant. Okay, and these are people who, it's like they talk and you think, oh my gosh, right? How did they know the answer to that? But it doesn't work, because eventually they all go away. All right, and the whole point is what am I supposed to do? Okay, because here I am, and I'm not a guru. And so I can never pull that sweater off, okay? And so I'm not a guru, so what do I do, right? I need equations, okay? Equations are my crutch, all right? I need equations. The equations are how I don't need to be a guru. I can use the equations, and using the tools of mathematics and computers and high-speed digital computers, I can crunch, and I can figure things out. All right, and I can figure them out because it's been codified in some particular way. So when we say that even physicists can understand knitting, this is a very low bar. It means that some kind of knitting, we can write down some kind of equations that are useful for us. The knitters know how to make this stuff already. Okay, it's like something I saw in Wired magazine, right? Which is some genius mathematician in the 19th century figured out how to hold pizza, okay, right? And so if you hold pizza like this, it droops and you can't get it in your mouth. But if you bend it the other way, perpendicular, it sticks up, okay? Oh my gosh, is this the Kobayashi Maru test? No, okay, there you go. All right, so here you go, right, here's the pizza. So what mathematical genius did this? It didn't require this guy to figure out for everybody how to hold pizza, right? All around the world, people hold pizza like this, and various things that are like pizza, scallion pancakes and crepes and stuff like that. And they managed to eat them without having ever learned this mathematics. The math is kind of overkill here, but it's one of those things where you say, oh, the mathematicians say, now I finally understand how to eat pizza, okay? And who's the guy? His name was Gauss, okay? And here he is. A picture of him, and I think he's smirking in this picture, okay, kind of like Mona Lisa. So here he is, and Gauss came up with this great theorem in 1825, which I just taught last week in class, actually, right? The theorem egregium, okay, and that just meant it was really impressive. And he wrote it in Latin because that was what people did, and we translated from Latin literally. Maybe this is Google Translate maybe, 5 years ago, but I don't know how Google Translate learns Latin. But I guess there aren't a lot of Latin websites, right? Okay. You'd be surprised. Okay, all right. The liturgy, right? The liturgy must have all been typed in. Okay. But basically what Gauss said is that curved surfaces stay curved unless you stretch them. And one kind of a curved surface is a flat surface. So flat surfaces stay flat unless you stretch them. And see, that's how the pizza works, right? Here, it's flat. And so it bends one way, right? It can't bend both directions. It can't droop this way and be folded that way at the same time, which we all know intuitively when we eat pizza, okay, and when you hold a piece of paper. Okay. So why am I telling you about Gauss? Well, it turns out this theorem that Gauss had, again, it wasn't like it was revolutionary to the people who knew what they were doing. And the people who knew what they were doing back then were the people who made maps. Maps are much older than Gauss, okay? This map is the Robinson projection. Does anyone know who paid for it? Come on, the first guess is the taxpayers, but no, but who paid for it? Not the king, no, it was National Geographic. Okay, National Geographic said, we want to have a map that sort of characterizes the world, and it doesn't do too bad a job of stretching things or bending things, but you see what the problem is, right? We know that lines of latitude and longitude are supposed to meet at 90 degrees, but they don't in this map. The other thing is, Greenland isn't this big. And here's the dead giveaway. See this line? That whole line is the North Pole. The North Pole is just a point, right? It's not a line, okay? Look how big Antarctica looks, okay? But they're very clever because you know what you do? I'm always thinking when I say that, you know, Julia Child tells you that if you mess up your cake, you put powdered sugar on it. Well, this is what they do. They do the parts where it's distorted the most are over the Pacific Ocean. And the ocean looks the same, pretty much, right? Yeah, you know, French Polynesia gets this bad end of the stick, okay? It gets distorted a lot. But, you know, most of the things don't get distorted too much. And along the equator, things are not so bad. And yeah, it looks like, it would make Greenland looks even more tempting, doesn't it? Right, when it's big like this. Okay, but there were other projections prior to that. This one's from 1923. I love this one because it actually preserves area. The area of everything here is correct. It's distorted. The shapes are wrong. You can tell the shapes are wrong because these lines don't meet at 90 degrees. Oh my gosh, this line of longitude isn't even straight. It's not even an arc. It's wobbly. Look, these up here are wobbly. Okay, but it preserves the area exactly. And again, you see what they did? They make these cuts. The North Pole is just 2 points. 2 points and 1 point have the same area, right? And the South Pole is 4 points, so that's okay. And again, most of the distortion is happening over the oceans. And I don't know if it was prescient or not. Greenland's been cut in two. Okay? Just saying, all right? Okay, there's this one. This predates Gauss, okay? So this is proof that the map makers knew about this long before Gauss came along. You see, this is the Mercator projection. And people love the Mercator projection because the lines of latitude and the lines of longitude are always orthogonal to each other, 90 degrees, okay? They're perpendicular to each other, which is cool, but it really distorts the sizes of everything. And you can see, because it's supposed to be 10 degrees from this line to this line, and from this line to this line, and this line to this line, so it's stretching things as you go up. And so the northern part and the southern part look much bigger than they're supposed to be. But it has this cool feature that if you want to go 30 degrees north, 30 degrees from north. So you want to go east, right? You want to go, that's 0, 30 degrees. If you draw the line, that's 30 degrees. It'll be 30 degrees like this. 30 degrees with each of those lines of longitude because the lines of longitude are up and down. So if you draw something that's 30 degrees from here to here, you know, and you draw a line that, you know, you want to fly, you want to take a boat from Natal to Lisbon, okay, and that's about, I don't know, 30-ish degrees. You say, okay, I'll set my course at 30 degrees. You draw a straight line, and then you set your compass on your boat at 30 degrees. It'll work perfectly, right? It's not the shortest path. It's not great circles like you see when you fly in planes, but it's called a rhumb line, R-H-U-M-B. Lots of extra letters, but it was a giant boon to navigation. So having this map allowed you to figure out, roughly speaking, what direction to go from one place to the other. Now we know that the real representation, but what's the message? Either you mess up perpendicular, So you mess up the shapes. Or you mess up the areas. And, well, okay. Is there some way of doing it where you don't mess up the shapes and don't mess up the areas? And Gauss says no. Because if something's curved, the only way to uncurve it is to stretch it, which means you have to distort it. Okay? Of course, we know this is the best representation, or a representation. So here's a representation where it's a globe. If you take this globe and now the areas are all correct, and the shapes are all correct, right? But if you try to take this curved thing and flatten it, make it uncurved, then you necessarily have to destroy the shapes of things. Okay? So that's Gauss's theorem. But the map makers do this, right? And they're even older maps than these. Okay? They had maps for a long time. Okay. But this doesn't stop us. Okay? It doesn't stop us because we know that you can take a piece of tin foil, which is flat, and you can use it to wrap a bunny. Okay? Now let me show you how they do this. Have you ever seen them do this? Okay, here we go. Here we go. Okay. Here's the bunny factory. Okay? And here at the bunny factory, the chocolates come along and they're I feel like how it's made, and right, and you keep going along, and then there's these special devices that put the tin foil and they crimp it and they rub it gently. Oh, sticker, okay, the sticker, okay, and then the bunnies come along. Here's the important part, and they came off backwards, so for some reason they have to be turned around. Okay, all right. I guess it's just too disconcerting for the bunnies to be going backwards. They should see where they're going, right? No animal cruelty at the Lindt chocolate factory, okay? And then they have to, and then these people come and they put these ribbons on. And you think about it, chocolate kind of, milk chocolate melts not so much different from your body temperature. So this room must be really cold, right? It's because they're handling them. And you say, oh no, they're not handling them too much. Mainly it's the machine. But watch, okay? The big ones, they didn't build a machine. Okay, these are lovingly wrapped, okay, by experts who are basically doing the same thing. But you see, when it's all done, you've wasted some tin foil. You need to use more tin foil than you had. And if you wanted to make something even more complicated, it would be even harder. Okay, and so you can take flat things and wrap them, but then they're all crinkled up. Okay, let me give you another example. Okay, this is an origami example. Okay? Can you make this bunny out of origami? Okay, origami is very strict, very strict. You can't cut the paper. You can't tape the paper together. They have rules. Do you know why they have rules? Anybody? Also because they merged their craft with the German craft of napkin folding. And if you cut napkins up, it's a mess, right? We'll talk about cut paper. But anyhow, there's this guy, Tomohiro Tachi, who made this software called Origamizer, which says if you want to make this bunny, you have to make all these little folds on a flat piece of paper. The program does not tell you what order to make the folds. It just tells you make these folds. And you can see something very disturbing to me, at least. The folds are much, much more fiddly than the final construction. Right? You have to do things at a much smaller scale. Right? And I don't know if you mess up what happens. And suppose you wanted to pre-paint the nose on this flat piece of paper. I don't even know which side the nose is in. Is the nose on the back or the front? And even if I did, I don't know where the nose is or the ears. Right? But here, watch Tomohiro Tachi himself fold it. Watch the sun go from one part of the room to the other. Ta-da! Okay? He had to put all these clips, like when you get a complicated haircut, right? Clips in, right, to do things. And finally you get this money. And this is barely good for anything because it's all filled with paper, right? You couldn't stuff it with candy like the chocolate ones, right, with the chocolate bunnies. So here you have this bunny, and it's called the Stanford bunny because some computer graphics person at Stanford decided to take an image of their terracotta bunny in their, from their, what's that called? Their garden. Okay, all right. And so that's one way of doing it. Now, a while ago, we thought, this is very difficult. You have to do things where the construction, where the folding is very high resolution compared to this, which is sort of a shame because, this, I guess you could tell this is a bunny, but, this is a lot of work for this. We saw this paper by these three French people. N'était pas un piece of paper. I don't know how to say it in French. But this is not a piece of paper, right? Why is it not a piece of paper? Sorry? Oh, that's good. But no, I understand, yeah, not the Magritte reason that it's not a piece of paper. Why is it not a piece of paper? Because this is not a flat piece of paper. No flat piece of paper could do this, right? And let me show you what I mean by that. The piece of paper actually gets a little narrower. The number of rows this way, or columns, changes as you go from this side to this side, right? And what's happening is that all these hexagons, you take two of them, and you take one and you make it into a pentagon, and you make the other into a sevenagon. Okay? See, it's 7 sides, right? This is like a little pointy thing. This is like a saddle. And these two things together actually allow you to fold the paper into the third dimension. Okay? And this is how you get around Gauss, because you're distorting it. Look, that hexagon sure is messed up. All right, it's a pentagon, and that hexagon's messed up. Here, watch carefully, okay? So if you're an origami person, you know it, or even if you're not. It's funny, I was in Japan, and I asked people, who here does origami? Nobody raised their hand, right? How about here? Who here does origami? Right. In Japan, they have a much higher threshold before they say they do origami, right? So apparently, because I couldn't figure it out, there's room, right? And so anyhow, okay, M means mountain fold, it means you fold down. And V means valley fold, it means you fold up. And what we're going to do is we're going to cut out this wedge of paper. We're going to remove this piece of paper. This is called kirigami instead of origami. Kira means cutting, right? And I'm going to glue the edges together. And when I do that, you see it's very easy. You can see that this hexagon, I'm cutting out exactly 1/6 of it. But I'm doing it in a funny way. I'm not cutting out one pizza slice. I'm cutting perpendicular to the pizza slices. So watch carefully, okay? This was done here, right, at the University of Pennsylvania, in David Rittenhouse lab, before the renovations. And doing mountain folds. It took us a long time to figure out how to do a valley fold. How do you do a valley fold? Oh, and then we thought, oh yeah, we can use a tool, right? We use a straight edge, okay? And look at that. Now the hole is sealed, okay? Not only that, watch Daniel Sussman use one finger to hold the thing together. All you need is one finger, one staple, one piece of tape, right? One wad of chewing gum, and the whole thing stays together, okay? There's an entire international organization, right? It's I don't know, it's conspiracy. It sounds weird. A secret international organization that uses this as their business model. IKEA, right? All right. So you go to IKEA and you build something that your children are supposed to sleep on. Okay, and you build it, and you have those funny tools. They give you that one tool. They don't give you the other tool. They don't give you the pliers that you need to pull things out that when you accidentally put the dowel in the wrong hole, right? Okay, and so they have these tools, and you put the thing together, and your kid's supposed to sleep on this, okay? And you put it together, and it's going like this. And they say, oh no, you're not done. There's this piece of cardboard and these little nails, right? Nail that piece of cardboard onto the back, right? And it's a piece of cardboard. And then suddenly, the thing's rigid as crazy. It's like it works perfectly. Because what you're doing is, instead of making it strong by having, metal brackets or flying buttresses, what you're doing is you're taking a piece of cardboard and you're using that, and using the fact that you can't shear cardboard. It's hard to shear cardboard, to slide it sideways like this. And that's what's holding everything together. And so IKEA makes all their money by making furniture like this. That's the whole flat foldable thing. Let me show you another one, okay? This one's a little cool. We call it the glide. We're just going to make a long slit along this line. And we're going to cut out 2 little triangles. Okay, here's Eagle Cho, right? Going ahead doing this. Again, this was done at the University of Pennsylvania. And he does the folds. And you don't have to watch the whole thing, right? We cut for time. And then look at this. He puts it together, and you get a nice 3-dimensional structure. And the 3-dimensional structure is stabilized by the rigidity of the paper. And there are these 2 places where it's wrong, where you don't have hexagons. And there's another place there. But look at this. If you were a bug, an ant crawling on the paper, you would still think that this edge was the same length as all the other edges. Right? As you went around the corner, you would still measure the same distance. And if you asked how far apart are the centers, they'd be the same too. So this is like the smallest amount of stretching and distorting this thing. We're distorting it in the weakest possible way. All right? And by doing that, we can actually introduce curvature, right? And 3-dimensional structure. I got to show you. I met this guy named Yoav Shterman, who's a material scientist in Haifa, and he showed me these things. These are cloth. This is woven cloth. Okay? And you're saying, why am I showing you this woven cloth? Watch how he makes it. So when you weave, I don't know, is this called the weft? What's that thing that goes across? Weft. There you go. Okay. The weft goes across, and that thing is the shuttle? Yep. Okay, the shuttle. Okay, here, watch one more time. All right, there's the shuttle. But he actually makes a reed that makes it so, you see, he's not pulling the strands straight across. Did you see that? All right. The strands are not being pulled straight across. They're being following this red line. They're coming like this, and they're going like this. And so after it's done, he gets this funny thing where it's woven correctly everywhere except for here. There's this funny little part, because there was a part where he was following the shape, and then he stopped following the shape. He did regular weaving again. Okay? So what do you think happens? He can fold it. Just like origami. Or rather, just like kirigami. This piece that's missing, this piece that's softer, that has less yarn in it, which was had 50-degree angle before, that's like a hole. And he's closing the hole. It's not exactly a hole that's that shape, but it's a hole. And you close it, and there it goes. Right? And the red is just for your eyes, and there's obviously some kind of form, some kind of model back here, right, that they're lining on. So you could see, you could actually weave things, and they have this custom reed that they invented, I guess, to do this. So now you can have cloth things that drape over funny shapes, but perfectly fit it. Okay, so like, you know, your favorite car, your favorite airplane, whatever you want to do. Okay. So far I haven't really talked about knitting, right? And you can tell I hardly know anything about weaving, right? But let me tell you how I got into knitting. In France, in particular, but they do it everywhere, they do pleating. And pleating is really, really time-consuming. So you have all these cardboard patterns, and you take your cloth, and you roll the cloth up in the pattern, and you compress it, and you wait for a long time, and maybe you use steam or something like that. And when you're all done, you have a pleated material. Let me show you. Okay, here we go. If I press L, it goes faster. Okay, so here's this mold. Okay, and he has these old, that's what irons used to look like, people, right? These old irons. That's why they were called irons, see? Right? And then, right, he does this, and he oh my gosh, and he folds it up. Right? And this is a very simple pattern. Okay? And then time waits. This is after it's been rested and steamed and compressed, and see, it's been bound. Okay, and he unbinds it, and it's the same thing, and he unbinds it, right? And even that's hard. he has to use clamps, and he unbinds it, and here's the reveal. Look at that. He's made a pleated piece of cloth, okay, which can be made into a skirt or, whatever it is you want to make it into, okay? But that is extremely time consuming. And if you have more and more complicated patterns, that's also complicated. So about 15 years ago, more or less, I met Genevieve. Genevieve has a laboratory over at Drexel. It's closer to my office than this room is. And in that lab, she has knitting machines. Genevieve, when she was young, was a designer. And you could go to Bergdorf Goodman. Seriously, you go to Bergdorf Goodman and go to the Genevieve Dion collection where she made stuff. But she had this vision. I have to do all this fiddling, folding. All right, I have to do all this. She was into pleating. Okay, pleat. Okay, and you saw the weaver guy, with the shuttle going back and forth. And I know some weaving's faster or more robotized, right? You saw Tomohiro Tachi fold that bunny, how long that took, right? She said, "Oh my gosh, knitting folds for you." Right? You don't have to have somebody fold, right? Not only does knitting fold for you, these knitting machines are all over the world. There's, if not hundreds of thousands, certainly tens of thousands, right? Most of the things that you wear, your socks, your undershirt, right? your some underpants, right? They're made, they're knit, okay? And these machines exist, and she had this vision. I'm going to go and study how to design knit patterns that make 3D structures. Okay? And so here, right, this is just knit and purl. So the knitters here know what I mean, and then I'll tell you what it is later. This is called bistable. The movie's circling, but it just stays, you can have this thing and it either stays open or closed, and you can actually open each one separately. And let me show you. Oh my gosh. Are you all right? Okay. Hi. Okay. Let me show you. Oh my gosh, this thing's going to fall off. I broke it. I'm going to break your. Okay. She gave me this. We call it the magic scarf. Okay? Each panel has exactly the same number of knits and their stitches. Exactly the same number of stitches in each panel. Right? And they're all just knit and purl. It was done on a machine. This blue line is some kind of very clever thing with heat. You don't have to bind it off or bind it on because it just heats it, melts, makes it melt it. But the point is, each of these patterns is different. And they look very different. And look, they don't even look like they're the same size. Even though they're made exactly the same number of stitches. Thank you. Also, each one feels a little different. They have different amounts of stiffness. Okay? And different amounts of stiffness in the two different directions. And you can check, right, that the yarn is not stretchy at all. See, first of all, I'm touching it. Right? So it's not wool. Originally, she made everything out of wool. I bet you guys would like to see these. We have more of these. So here you go. You start. Pass it around. We have more. Okay. I'm going to hold this so that I can demonstrate it. All right. Scatter them about. Okay. You can toss them. They don't hurt. Okay. Okay. And what's cool about this is you've actually made a 3D fabric which has 3 dimensions. Nobody folded this. It folded all by itself. And these knitting machines exist all over the world. All right? If we could co-opt them into making things for us, right? We could rule the world. We could dominate the world by making 3-dimensional things, okay? So let me show you how a knitting machine works. All right? And the knitting machine's very cool. And I have to admit that when I saw the knitting machine the first time, I had no idea what was going on. In fact, It took me a long time to understand what was happening. Okay? So you have these needles, these hooks. Knitting is when you take a loop of yarn, or you take yarn, and you pull it from the back to the front through an existing loop. There are no knots in knitting. Well, there are, because technically speaking, the thing that isn't knotted is called the unknot. That knot has a name, okay? Because the mathematicians have to have a name for it, okay? You can't just say it's nothing, right? Okay, it's the unknot, okay? And so this is how knitting works. Knitting is pulling the yarn from the back to the front. Anyone know what purling is? You say it out loud. You. If knitting is pulling it from the back to the front, what's purling is pulling it from the front to the back. How would a machine like this pull it from the front to the back? It can't. So they add another set of needles. Okay? And the needles to do it. And then you can eat. So the carriage goes back and forth. And you can say, oh, but this is kind of boring. This is always going to give you knit, and this is always going to give you purl. But no, because you can have one pass where no carriage goes across, and the needles just transfer the loop from the back bed to the front bed. Okay? And in fact, the beds can rack compared to each other. So you can have missed stitches too, or if you want to. Okay? And you can have a missed stitch just by having the needle not go through. But I call it a transfer, but there's another word for it. Two loops go on the same. Anybody?
Knit two together.
You knit two together. Okay, good. We call it a transfer. Okay, knit two together. Right? So by doing this, you can actually put both loops on the same hook if you want to. And so you can do very elaborate things with these machines, right? They can even change the yarn midstream to change the color. All right? And it's the coolest thing. They do it by cutting it and having a little tornado blowing on them. It unravels the yarn. And then they bring them close together, and then they blow again, and it hooks them back together. No knots. Okay. So this is how knitting works. Okay? But this didn't help me. In the real machine, the needles are really small, and you can't actually see what's happening because the carriage is in the way. Okay? And here's a knitting machine going. All right? And you see, this is laboratory speed. If you go very fast, the needles break. Right? Now, the people who are making your t-shirts and your socks, they don't care about the needles breaking, they don't have needles. The laboratory goes slower, but look what happens. It just spits this thing out, and it's all folded already. You don't have to wash it, you don't have to block it, you don't have to, shake it up or anything. It just comes out, it's folded. This just came out of the machine folded. All the things you saw, they come out of the machine, all folded, all crimped, all like that. I don't know why I have another movie of it. It's cool. They're very loud, the machines. They go clackety, 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 clackety. Probably nobody remembers this, but there used to be computer printers that were like this with the green and white paper and right? You remember that? Okay. All right. So at this point, people say, that's really cool. There are these knitting machines. We know they're weaving machines. We know that, in fact, weaving machines were the precursors to computers, etc. Knitting machines. Are there any crocheting machines? Everybody always, right? They always want to push up. And so it turns out, yes. Right? It's just been invented, okay, by Tamar Nix. This is Tamar, and it has electronics apparently, right? And turns it on, right? It's like the beginning of Batman, atomic battery to power, right? And she there it goes, and it measures things in centinewtons. Oh, sorry, I forgot about the microphone. It measures things in centinewtons. Forgot all about it. And here, it's crocheting. Do you see? People who know what crocheting is would know that this is crocheting. All right? And people are asking me, how does it work? How does it know where the hole is? Right? Does it have a camera? It's like, I don't know. Right? But Tamar, this isn't a secret. This is not a secret. So one can find, if you, Tamar Nix, just that name, you Google it, you'll find her papers about this, where she built this. So she built a machine that can crochet. Whether it can do all the exotic things that you can do with crochet, I don't know, but it's a proof of concept. Okay. So when I was trying to understand knitting, I just kept going and talking to Genevieve and looking at the machine. And some people seem to know what was going on. I brought my kids. They knew what was going on. I had no idea. And then I started looking at these pictures. So this is a whole big swath of knit. See, knit. And here you have the loops going from the back to the front. And this is purl, which is just the backwards of knit, which is the loops going from front to back. And it didn't really help. All the exotic stuff that you see in the scarves there, that comes from when you put knit next to purl. If you just put knit together, it's not that interesting. It curls up. It's not fun. Same with purl, because it's the opposite of knit. It's just the back of knit. But this is where all the action comes in, when you attach knit to purl. In these things, obviously you can do things that are much more complicated. What do you call it? Two stitches together? Knit together, miss, okay? Things like that. And then, suddenly, it was clear to me, okay? So, before I got on an airplane, this artist we were working with, this artist who came to us because he liked kirigami, he came to us and he showed us this. He showed me this. He sent me this picture. And we're passing them around, and they're a little prickly because these are made of chicken wire. Okay? Here, bring one up front. Okay? And suddenly, I got it. Suddenly, for me, the bell rang. The light went on, whatever. The light, okay? Because suddenly I understood what knitting was. Forget about knit, purl as you go across this way and that way, because that's how the instructions are, right? I said, oh, no, you see, along this direction, I think that's called the course. Is that right? You call it the course, this direction? Okay, sorry? This is the whale, that's the course. Along the whale, okay, along the whale, what you see is that the pink and the yellow are just twisting around each other, right? In a nice little left-handed twist. And the next line over, the next column over, it's a right-handed twist, and then a left-handed twist, and a right-handed twist. And that means that you can actually put a scaffold in. The scaffold was everything to me, because with the scaffold was made of these things called helicoids, right? Which, you know, are fun pasta shapes or you know, things for stirring water. And these are easy for me to understand. I'll tell you why. It's because I'm a misspent youth, okay? But here it is. And you just have to attach these together, and you can use them as a template for knitting. And suddenly, to me, this was everything, because now this is the fabric. I understand that the fabric's really made out of the yellow and the red things, but to me, the surface of the fabric is now the scaffold. It's the negative space. It's the space that isn't the yarn. Okay. Watch carefully, all right? Why do I know all about this? My misspent youth was misspent with somebody in the audience, okay? I was a postdoc here 30 years ago, all right? And with Tom Lubensky, and we worked on this, okay? And we said, oh, see this? See, this is a helicoid. This is one of them. See it? Okay, pay attention, okay? All right? All right, here's another one. And I just put it next to it, okay? There's the third one. You know what I just made? The parking garage at 34th and Chestnut, right? You see? You see, here's the up ramps and here's the down ramps, right? You park like this, right? And you're kind of parked at a tilt and you're parked at the other tilt. And over here is where the elevator is, and you're never quite sure, am I on the second floor or the third floor? And over here are the stairs. And here is that little escape route, so you don't have to go all the way up to go across, right? You don't have to go all the way up to find the down ramps. You can cut through, you know? It's a parking garage, okay? And we were so fascinated about this. There's materials called smectics, and I could tell you all about them. I really could tell you all about them. So could Tom, we could tell you, we could probably write multiple volumes on it, where these layered things, in the real world, these layered things we're thinking about, these layers are only about a nanometer thick. Very small, okay? But the geometry is the same. And we were interested in how things like this and surfaces like this could be constructed This is an old surface called shirk surface. This surface, we said, oh no, it's not one big surface. It's actually built out of these little pieces, and each little piece we understand. And since each little piece here is exactly the building block we need to make knitting, that was everything we needed. We knew how, then, to put together any kind of scaffold we liked, to make knit and purl patterns as we liked. And the first thing they did, that Genevieve did, because they know how to make things, right? They're in material science. They made helicoids themselves. It's out of, I think it's called viscose, right? Okay. And they cleverly did something to make them twirl all by themselves. And they just made left, right, left, right, left, right. And then they just put, I mean, it's like a joke. They put yarn on it, right? But, big thick yarn. And the big, the big thick yarn goes over these things, and you can see this is a left-handed one, this is a right-handed one, left-handed, right-handed, and you see knit. The pattern's the knit pattern. And of course, in a real machine, in the real world, the yarns come very close together and they touch. But under tension in the machine, this is exactly what it looks like. Okay. And this is the back of it, which is purl. Anybody who doesn't know, you can check your sweater right away. Knit looks like strands going up and down, and purl looks like strands going left to right. You can check, okay? And it was cool. We built this. We still have this, right? It was a collaboration because Genevieve made this and had the yarn and had these garters, and I had these metal things that you use. They're called standards for doing experiments, right? The standards are still over in Drexel, okay? And so this is how you make interesting structures. So, most of the knitters in the room know this, but it didn't occur to me until I started working with the knitters, that when you have a sweater and you have the cuff, you don't have less yarn in here. You've just changed the pattern, and the pattern makes the cuff smaller than the rest of the sweater. But you don't have to sew a cuff on, right, or make a cuff on a different machine. You can have it be all on the same machine. And this rib pattern where you have knit and purl next to each other, this is what gives you the rib pattern. It has some other name. What's the other name? Stockinette. Okay. It turns out that the commercial knitters, the industrial knitters, the knitting machine knitters, and the hand knitters have a completely different language. And so it's very strange, right? It's I don't know why. You'd think they could share a common language, but they don't. Of course, machines can't do what hand knitters can do. Not all machines are limited in the things they can do. They can't twist the loops like hand knitters can. Okay. Then we wanted to make a two-bed system. We wanted to put knit and purl together. We wanted to see, could we make rib? Okay. And so here we have, it's hard to see, but we have two beds. We have a front bed and a back bed. We have a set of helicoids in front, and we have a set of helicoids in back. One's the back bed, one's the front bed. And we have it under tension. And then we release the garters, and we do an experiment. See the experiment? Now you see, how does this pattern of knit and purl, right? You do knit on the front, and you do purl on the back, but they're connected, right? How does that change the shape of this curtain? And you can see here is under tension, and when the tension goes away, the blue ones go forward, backwards, the orange ones go forwards. The ribs form all by themselves. But that's not because of the yarn, or it is because of the yarn. Of course it's because of the yarn. But we can also understand it in terms of the surface that's in our head. And so here's that surface. And we thought about this surface for a long time. Oh my gosh. When am I supposed to be done? Now? No, I'm too bad. All right, here we go. All right. Here's that scaffold. And you can see, here's the knit and the purl. What's really cool if you're a simulator, right? If you actually want to simulate stuff, this is really cool because you see this blue loop? This blue loop is on one side of the scaffold. It never touches the orange one. I don't have to worry about the blue and the orange touching. If you tried to simulate this, you'd have to make sure that the yarn never crosses itself. But here you don't have to worry about it because the surface keeps them apart. Okay? And in fact, you could just say, oh, it's enough actually just to study one loop on that surface. And then you can wiggle the surface around, and that changes the shape of the loop. I don't have to worry about the other loop. In fact, I started thinking about it, we started thinking about it, we started thinking, oh, you know what? It's as if this scaffold, so suppose you're this orange loop, the scaffold is the effect of all the other yarns on that orange loop. That's what's giving it that shape, right? And so you say, instead of thinking about the individual yarns doing it, you just think about the scaffold doing it. And then you say, well, what happens at the end of your fabric? At the end of your fabric, there's no more yarn over here. There's no more scaffold over here. The scaffold was clearly pushing this yarn forward. The reason it had this shape was because of the scaffold. And the scaffold was a stand-in, a proxy for the yarns that were there. And so that means that if you end, it's going to roll backwards. That side too. Right? Because the yarns were making it go forwards. Okay. What about the top and the bottom? Exactly oh my gosh. Woo. Okay, exactly the opposite. Here, the scaffold was pushing this blue loop, I think it's called a bite, pulling this blue bite back. Okay? So if you stop knitting right here, or stop, I don't mean knit purl, I mean the process of knitting. If you stop right here, there's no more fabric, there's no more yarn here, so there's no more scaffold here, and so this will move forward because this scaffold was pushing it backwards on the top and the bottom. Is that true? Yes, it's true. If you take a patch of knit, it rolls forward on the top and the bottom, and it rolls backwards on the sides. And of course, purl does exactly the opposite because it's just the back. In fact, if I remember correctly, this picture is the same picture as this. It's the same piece of material. We didn't take them at the same time. Okay, we took it, we flipped it over, okay, and took a look at that. Okay. But now you have the scarves, okay? And here you have the scarves, and by just changing the pattern of knit and purl, where the knit and the purl are, you get totally different patterns. That's all you're seeing in those scarves out there. Okay, it is just changing exactly where knit meets purl. Because let's think about it, okay? When knit meets purl, knit, if you attach knit to purl, knit rolls backwards and purl likes to roll forward, so they roll over each other. Right? You see? You know what this is? What? Okay. It's also a spring. And you understand? This spring has nothing to do with the elasticity of the yarn. It's not elastic yarn, right? You could imagine designing a much more complicated pattern so that the spring reacts differently. The first 3 centimeters, it has one kind of force, and then you pull it a little more and it has a different force, just by how you make the pattern on it. So the other thing that Genevieve, remember she said, not only do we not have to have people fold all these things meticulously, we can start making fabric into a material, not a material for clothing, but a material to build things. Because here's a spring, right? People are going on and on about 3D printing, blah, blah. You know, see their 3D printers? Here at Penn, have you seen a 3D printer? Yeah. These knitting machines already exist. They've existed for many, many years. And not only that, there's probably millions of people hours invested in knowing how knitting works. All those people who really know how knitting works can make things. Right? They can use their experience and their skills. You consult the gurus, and they can actually then help you design exactly the kind of thing you want that has exactly the kind of mechanical behavior you want. So what did we do? Right? We thought about this for a while. We thought, well, suppose you make this little thing, knit, purl, little pattern like this. So knit, oh my gosh. Knit rolls over purl, when it's side to side. Purl rolls over knit, top to bottom. Knit rolls over purl, side to side. Purl rolls over knit, top to bottom. And so you get this thing here, you know, it's like a belly button, okay, that comes out, right? My father would have called it a pipik, all right? It comes out like this, right? And it comes out, and you make this little twisty thing, and if you make it twisty enough and have enough of it, you could make a button, You could use it as a button, right? And people do that. And so it's cool. You can start thinking, oh, I can start piecing these things together without knowing what I'm doing, right? Without knowing about the details of the fabric, of how the material is made. Oh my gosh, right? Without knowing about the details of how the material is made, I just know if I take a patch of knit and a patch of pearl and do this, they will roll over each other like this. And it'll have a certain elastic beat response. Not only that, this does not depend on the fabric, on the yarn you use. This works for wool and for cotton and for nylon. All of them do it. To different extents, yes, they are stretchier or not stretchy, different extents. The wool ones make you itch. The cotton ones breathe. Oh my gosh. Okay, the cotton ones breathe, and you can do stuff. Sorry? Oh, are we good? No, don't fix it. It's okay. It's exciting. Okay. All right. All right. So here's the knit and the pearl. And the thing is you're now predicting the curvature of these things just from how the thing is constructed. Again, Genevieve's point. There's the part of the fabric that has to do with how it's constructed, and there's the part of the fabric that has to do with the material properties of the yarn. And we're trying to separate that out. This is how even a physicist can understand it, because we don't have to know about the yarn. And we don't have to know about whether it's itchy or scratchy or nubby, right? Okay? And lo and behold, a guru comes, all right? Guru comes and says, oh, but you know this picture you had about the edges are not, it's more than just the edges, okay? Because in fact, everywhere in the knit fabric, you have one strand crossing over the other. Remember what I told you? I told you this on purpose. On the knit side, the yarns go up and down. On the pearl side, they go left to right. Every knit stitch looks like this. Pearl stitch looks like this, but backwards. Okay? So, because the yarn's under tension, they pull. And that means that they actually want to make a little saddle. You see? The surface between them would like to be a saddle. Left to its own devices, each of these little crossings would like to be a saddle. If it's a knit saddle, it wants to go one way. If it's a pearl saddle, it goes 90 degrees. So the knit saddles and the pearl saddles are fighting with each other everywhere. And there's the other thing, which you can see from the scarf. The knitting doesn't like to stretch because the knits are tightly put together. So they don't like to stretch. But you know, do you remember I told you this? You can't have something be curved and flat at the same time. And the only way to have flat go to curved is to stretch it. Okay? And curved go to flat. So you have this constant tension between the local desire to make this curve, but the global desire to just be a big old flat sheet. And you saw that in the middle of the patch of knit. It was just flat in the middle. And it was just flat in the middle of pearl. In the middle of all these things, it's flat. All right? And so my guru came, Lauren, and she said, oh, I know what to do. Okay? All we need to do is we need to model this exactly the way we just described. You say, every place, I can't remember, is red pearl? Red is knit? Okay, doesn't matter really, right? Red is knit, blue is pearl. It doesn't matter. I got to tell you the coolest things about the machines when I finally watched my daughter knitting. You know what the coolest thing about the machines is? They go back and forth. They don't have to flip the fabric over, right? they're by what's that word? Ambidextrous. Okay, and so Lauren said, okay, all we'll do is we'll say these red and blue, the red and blue thing, they don't like to stretch. There's some energy penalty for stretching, and there's some energy penalty for not bending the way you want. Right? So they don't like stretching, but they also are upset when they don't get to be those little pieces of saddle. And those two things aren't compatible. Gauss told us that. Of course, Gauss didn't invent that. People knew that forever. And so Lauren did a simulation. She took software that existed for a completely different application. And look, they all folded. And Lauren said to me, oh, could be a coincidence, right? And we tried it. Every pattern in that scarf, if you use this program, folds exactly the way the program suggests. Not only that, here's the best part. It doesn't really matter what parameters you use in the program, okay? It doesn't matter exactly how hard it is to stretch compared to how hard it is to bend. All that matters is that you count both things. A piece of paper is one where it's all stretch, where the hardest thing to do is stretch. Bending isn't so hard for a piece of paper. And you can have some other limit where it doesn't mind stretching, it can just bend and do whatever it wants, like a soap bubble or something. But this, oh my gosh, is different. Soap bubbles don't like stretching either, just in case it's on video. Okay. But here, you say both of them are there, and not only does that mean that we don't have to go in any of the details. See, another thing physicists don't want to do. We don't want to know any details, right? It also explains why every kind of yarn folds the same way. It doesn't matter what the yarn's made of. The fact that we don't really have to fine tune. It's not like we had to go through some giant parameter space and find exactly the right ratio of stretching to bending to get this to work. Of course, this is coarse. When you look at the real, scarves, the folds are much sharper than these because they fold along the lines of where the knit lines are and the purl lines are. But we were happy. We were happy that we could pick 7 different patterns and they all folded exactly the right way. This is the small step that it means that a physicist can knit, all right, is that we can make something where we didn't have to know ahead of time what was going to happen. Now that you have this, you can now go backwards, and now if you have a target, instead of having to knit many, many different things to try to get that target, right, so now you get to combine. You get to combine 10 million years of expertise along with this computer program, and together you can then try to steer and get the shape you want, for whatever shape it is. You want to make those cool springs or whatever it is you want to do. So let me end by showing you these two gurus. Once we started being able to talk to each other, it took us probably 9 years before we could actually understand each other, right? So she's French Canadian, but that's not why. It's not. It wasn't. She's Canadian. It's not the language gap. It wasn't just the language gap between machine knitters and hand knitters. It was the language gap between physicists and people who actually know what they're doing. Okay, and so we were getting all into it, and suddenly they made this. They all got it, and they made this, and they handed it to me. See, this comes out flat, and then it folds into this creepy smiley face, right? Which is sitting in my office. So we need to get all the scarves back, right? And thank you for your attention.
So we have some time for some questions. I've got a couple team members with microphones if anybody wants to pose a question.
Yeah, go ahead.
I'm concerned that the friction between the yarns isn't more important, because when we actually produce fabrics for use, the friction provided by silk or cotton or different animals' yarns makes a big difference.
That is exactly correct. It's very complicated. There's a world's expert on that sitting in this room, all right? But let me just say, all right, let me just tell you the dumb physicist answer, okay? You know when you take your sock and you stretch it and it comes back, right? It comes back to where it started. So I would say when you stretch your sock, I mean not a lot, you stretch a little bit, the yarns don't slide past each other. To the extent that they don't, that's because of the friction. Different materials are better at holding their shape, right? And that's absolutely right. And we can actually run, what's that stuff called? Fishing line through the knitting machines, right? And you get something that's really uncomfortable, totally different. So you know what's the weirdest part about fishing line? Is that fishing line, if you twist it over here, it twists over there, right? So it actually transmits information very long distances compared to the yarn. So yes, this is where the material property is important. That's why we can't just do this if we want to make bespoke materials that do what we want. And what's that stuff? They coat them with Teflon, or they Snuggles. Yeah, they use fabric softener, right? And you can take these things and wash them and put fabric softener, and then it changes their behavior and it changes their shape also, right? Because once they can slide, then they relax. So yeah, the friction is really important, and the friction of different materials is different. And you know, it's a weird thing. The world expert will tell you that when you stretch fabric and then you let it relax, it's not the same. Even though it comes back to where you started eventually, right? It's different on the stretching and the relaxing. And that probably has to do with those frictional differences, among other things. Yeah, so you're worried about it. That is why this is so complicated. Yeah, okay, I started with that. I said, see, we can barely understand this part, just the shape part. Yeah. Okay, go ahead. Oh, no, you have to ask.
Did you also look into circular knitting? I guess the surfaces would be there, but maybe with a twist.
Yeah. So there's nothing here that would prevent us from doing circular knitting. Circular knitting is how they make socks, right? Circular knitting machines only do purl or only do knit, depending on what your perspective is, right? All right. So they only have one set of needles, but that's enough, right? I think Genevieve told me that like 85% of the things that we wear only need a circular knitting machine. You don't actually need knit and purl. Knit's enough. Knit and those stitches to bind two together and misses, that's enough to make a lot of the things that we wear anyhow. Other questions? No, what, you're whispering. No? Oh, okay. Okay.
Okay, pop quiz. What's my sweater pattern?
It's the alder sweater by the crayon.
Yes! I knew someone would get it. Okay, thank you so much. We will chat and have more questions before you leave if you want, but really enjoyed this tonight, and thank you all for coming. We'll see you at the next Science Cafe.